In the second half of the lecture, we're going to look at some more applied examples. We're going to look at some particular buses, some particular devices. This is kind of the nerdiest part of the whole module. We really are going to spend half an hour learning about different kinds of wire. This is what your non-computer science friends probably think we do all day. Come to a lecture and learn about different kinds of wire. It's useful though because when those same friends ask you to fix their computer, this is often the kinds of things you're going to be doing. So it's worth spending a bit of time looking at what is actually out there. So, in the 8-bit era, there were lots of chips with everything. Every ROM unit, every I/O module was physically a chip sitting on the bus. And you could see where the I/O modules were, where the devices were. It also made the economics of the system much easier, because if you were a computer designer, you could buy in the CPU, you could buy in I/O modules and devices, and it was very clear who was making what and who was putting things together in different ways. Nowadays, all of this stuff is probably going to get shrunk onto a single system on a chip now in a lot of the 2019 devices, in your phone, in your Nintendo Switch, and so on. So the economics are a little more complicated. We're really seeing hardware design becoming a kind of software design now. If you buy your CPU from ARM, if you're the computer maker, you don't take a lorry load of chips with CPUs on them. You buy a license to use ARM's IP. That's going to come on a disk as a file describing the layout of a bunch of transistors. And you're going to buy licenses for your CPU and for your I/O modules and even for your RAM and your ROMs. You're going to buy all those licenses, take the digital descriptions together, and you're going to put them together to make your custom system on a chip, and then you're going to arrange for the manufacturing of that. So in the 8-bit era, there was usually only one bus as well. It would come out of the CPU, it would go to the RAM, the ROM, the I/O modules. Nowadays, we're moving to these hierarchical bus architectures. In some cases, you might have 3 or more buses now. You've got your main system bus coming out of the CPU via a cache. This is what you use to talk to main memory. And then you're going to have some kind of bridging system to take you to other buses. So you might have a bridge here that takes you to what's called a high-speed bus. So here you've got things that are kind of intermediate speed devices, like your SCSI hard disk, your FireWire, graphics card has to go fast, networking has to go fast. And then you might have things coming off of that bus to an even slower expansion bus, where you're going to dangle slow devices like a modem or a serial port or even a fax machine. Apparently, the number of faxes being sent has gone up this year for some reason. That's a mystery. So you will typically find this instantiated by this North Bridge, South Bridge architecture. Like the architecture of Edinburgh, we have a North Bridge and a South Bridge. The North Bridge is going to sit here, it's going to talk to the CPU. It's going to manage this fast bus. Maybe you're going to put some cache on here. Historically, this would have been a level 2 cache with level 1 on the CPU. Nowadays, level 2 cache has probably moved to CPU. Maybe you've got a level 3 cache here. Maybe that's even moving to CPU now as well. And it's also going to manage an interface to a slower set of buses that are handled by the South Bridge. These are going to appear as physical chips on your motherboard on a desktop PC. So a recent trend has been things migrating up the bus hierarchy. We used to dangle most things off the South Bridge, so you'd have things like PCI bus was the definitive place to slot in all your expansion cards, your graphics card, and so on. Some of those things are now migrating to be compatible with North Bridge level and North Bridge speed, so you probably find your graphics card nowadays sitting up here, and you might also find your PCI Express cards. This is an update of PCI that has migrated a whole bunch of stuff from up there to up here. Then you have the slower stuff still hanging off the South Bridge, so something like a USB interface could hang off there. USB is another level of bus, and that's going to have even slower devices sitting further down. The North Bridge and the South Bridge are becoming bottlenecks in modern computers now. Again, you can run into problems if you try and hot rod your computer by upgrading the CPU, getting your water cooling and everything. You can move the bottleneck from the CPU to North Bridge and South Bridge. So we're seeing a lot of recent architectural work on upgrading these devices now. We're starting to see Northbridge and Southbridge with their own fans and heat sinks. This stuff's important when you're overclocking your computer. If you overclock your CPU, you might need to overclock your Northbridge and Southbridge stuff, and again, try not to melt them. Remember, these things have to be cooled as well if they're going to go really fast. So this is what things can look like in a typical, fairly modern machine. So we find a big slot for the CPU, then we see the Northbridge with a bunch of cooling stuff on it. We see the Southbridge sitting down here, and we see the slots. These are, I think, PCIe slots, probably hanging off the Northbridge in this case, and PCI slots hanging off the Southbridge, where we're going to plug in our physical cards to put in our extensions. So another recent trend is this move to more standardized I/O. You notice when you plug in a USB device now, you can get a lot of information about that device before you have installed a device driver. So if you plug in a new webcam onto your Linux machine, you can type dmessage to get information, and it will say this is a Logitech C920 webcam and so on. That information can already flow over the USB bus without the need for a device driver. This is done through the hierarchical architecture. It's done by making the USB system act as a single I/O module. Then everyone using the USB bus uses the standard USB protocol to communicate. The reason this is nice is because it makes the I/O system much simpler. In the 1990s, especially if you were doing audio computing, doing computer music production, you would very quickly run into IRQ hell. This was the window from hell on a 90s computer music setup. And what you see here is a whole bunch of I/O devices. They're mostly sound cards, music keyboards, other audio devices. And every one of these devices needed its own I/O module and its own interrupt request line. And your CPU had a physically limited number of IRQ lines. Remember, they're actual wires going into the CPU. And so you reached this point where you ran out of IRQ lines, and then you had to start doing all kinds of dirty tricks, like trying to convince two devices made by different manufacturers to share an IRQ line and to convince the system to work out which one it was coming from. Or sometimes you try and hot rod your machine by disabling IRQs from other parts of the machine that you thought you weren't using so that you could put them on audio systems, and then bad things would happen when you ran out of IRQs. So we probably spent more time doing this than actually making music at that period of the 1990s. We're very lucky now to have this USB system where you can buy as many sound cards as you like, and they're all USB, they all fit on the USB bus, and they're all going to end up sharing a single IRQ that's coming from the USB system as a whole. Today we see a whole hierarchy of different buses, all running at different speeds, all for different purposes. We can measure these things in bandwidths, in gigabits per second, for example. So we have slow buses, things like USB is sitting towards this end of things. Even gigabit Ethernet is relatively slow compared with the buses you find inside a computer. SATA is a bus used in your hard disk connection. This is your memory. This is DDR4 RAM we discussed. This is PCIe. We'll talk about InfiniBand later. This is the PlayStation 4's own memory bus. It's currently leading in the hierarchy. And the world record is 26,000 gigabytes per second. That's 26 terabytes per second if you're using optical systems. So probably most of your desktop machines will have slots like this in them. This is PCI Express. This stands for Peripheral Component Interconnect Express. It's an evolution of an older standard called PCI. It's related to an old graphics standard called AGP. You see it comes in physically different sizes, so these are buses with different widths, different numbers of wires, going all the way from 1 bit to 32 bits in what's called a lane. You remember the motorway lanes? These are the lanes of the bus. Comes in different speed versions, ranging from 2 gigabits to 16 gigabits per lane. PCIe is not technically a bus, it is technically a mesh network because it has some of these properties of mesh networks where you can do forwarding of messages. You can have devices sitting on this bus that are somewhat intelligent. They can recognize where a message is intended for, and they will forward it only through one part of the network rather than it being a true bus where every message has to go on every part of the network. So this is a general current design trend. A lot of things we think of buses are kind of evolving into more mesh-like networks. So you've probably all heard of USB, the Universal Serial Bus. Bus is very much in quotes here because USB is not a bus at all. It's a completely misnamed technology because, of course, it's actually a point-to-point connector. The USB cable has one master end and one slave end. It's not a bus. It's not a public place where people share their messages. It's really intended as a modern version of the serial port, what was called RS-232. There's a way of a master device communicating with one slave device. USB has been very useful in replacing a whole range of earlier interfaces, right? We used to have this, especially in computer music, this problem of lots of different devices all needing their own I/O system and their own IRQs, and USB's given us this very convenient interface where everything can work in a single system now. It's been handy to send power over these devices. You probably use USB cables to charge your phones. And the USB protocol includes this basic layer where you can get simple information like the name, the manufacturer, the model of a device without needing any device drivers. So this enables you to plug your webcam into Linux, and Linux can see just enough information that says this is a Logitech C920 webcam, and that's enough information for Linux to go off and find the device driver software and bring that in. In the old days when you got a new device, you had to find the CD-ROM for that particular device and install the driver before you could talk to the thing at all. So USB has gone through a bunch of different iterations from USB 1 to USB 3. We've seen speed improvements, so we're on around 5 gigabits per second now. Something of a limitation of this setup is the master-slave protocol. There's always what used to be a desktop computer was in charge and your device was the slave. This has become a bit of a problem with devices like phones now because your phone is usually the master device, but then if you connect it to a bigger machine like your desktop to transfer data on, you want it to appear as if it's the slave device. So you want it to play two different roles but using the same bit of cable. So it's the reason why it's a little tricky to say run a desktop PC's USB sound card off your phone. Again, if you want to do computer music on your phone, you need to turn your phone from being a device into being a master. So you can do this. There's something called the on-the-go protocol that turns slaves into masters. You can make this in charge of the USB network, but you'll need a physical thing to plug in there and swap the directions of the sockets over. There are USB hub devices. These things will emulate multiple ports, so you can have a hub coming out of one USB port on your phone to have 4 devices coming off there. That's still not a bus. It might look like a bus if you've got 4 USB devices all dangling off a hub, but it's not running as a bus. It's only emulating the multiple ports, so you don't have this property of every message being visible to everyone. It's still just a point-to-point protocol underneath. USB is also famous for its annoying connectors. We've seen a lot of different standards for what should go on the other ends of these, which means everyone has to carry 4 different bits of wire around to recharge people's phones when they come to visit. The new one is finally bi-directional, which they've copied off the Apple design, so you don't have to faff around in the dark figuring out which way to plug the thing in. What's happening inside USB then is there are 4 physical wires. If you cut open a USB cable, you'll see the 4 wires. 2 of them are carrying power, 0 and 5 volts. You can use this for charging your phone or sending power to your device, like your printer. The other 2 lines are used to send the signal. Now, unlike the buses inside your computer, USB is designed to go outside your computer into the real world, especially when you work with robotics and you put these on a robot. Your wires could be traveling around in the presence of big magnets, like the magnets on the motors of your robot. And if you only had 1 wire containing the signal, there'd be interference from all these things in the outside world, especially from motors. which would distort your signal. So USB is using a system called differential voltages to represent its signals. These two wires in the center, they both send the same information, but they send it by flipping the direction of the voltage. So when we send a 1, this line goes up and the other line goes down. When we send a 0, this line goes down and this line goes up. But they both move together. They're equal and opposite directions. So that means the information is stored in the differential between the two voltages, rather than the absolute level of the voltage. And that makes it immune to external electromagnetic fields. So you can happily run your USB cable right next to the motors of your robot without the thing getting distorted. Especially when you twist the wires together, you'll see these two wires are physically twisted to maximize this effect and making it immune to external fields. FireWire was set up as a competitor to USB. FireWire is actually Apple's trademark for a more generic standard called IEEE 1394. Everyone calls it FireWire. Initially, it can look a lot like USB. You'll often plug in a sound card via FireWire. But unlike USB, FireWire is a true bus. So in particular, you can see here we can daisy chain FireWire devices together. You can't do this with USB. USB would need a separate cable from the master going to each of the slave devices. But with FireWire, they really are sharing a bus. So this device will see the signals and it will pass everything on. The same messages are going across the whole bus. And every message has an address saying which device you want it to go to, and the devices are listening for messages on their channels. There's a nice collision control protocol built in here. Again, unlike USB, there's no notion of a master and a slave here. So any device in a FireWire bus can take on the master role. There's a protocol where they negotiate who's going to be in control of the bus. And then when you take that role, it's your job to make sure that people aren't speaking at once and trying to write too much stuff on the bus at the same time. SCSI and SATA are two bus protocols which compete for usually hard disks and other mass storage device interfacing. SCSI is the older one, very ancient, classic, dating from the 1980s, but as a result is now very reliable, very robust, very well tested. And so it's still used in higher end machines. It's a more expensive system, typically used in servers, things that really have to work. SCSI was interesting in the 1980s because it pioneered this notion of taking work out of the CPU and putting it in the I/O module. Until that point, a lot of this work would have to be done by the CPU, controlling timing and error handling. And SCSI created this idea of making the I/O module behave in a more CPU-like way. It offloads a lot of the work from the CPU. So your 1980s SCSI machine is going to run faster than everything else because the CPU is freed up to actually do computing rather than wasting its time on I/O. SCSI continues to evolve. The latest update is the serial storage architecture, and this is representative of a general trend of buses moving away from being parallel buses to being fast serial buses. So when I was a kid, buses had lots of wires. You had these big ribbon cables, and a general trend now is for everything to look like USB, just with one or two wires containing the signals, but going very fast. So SATA is the cheaper version of SCSI. This is what you probably find in a consumer desktop. SATA is a highly recursive acronym which stands for serial ATA, where ATA stands for AT attachment, and then AT stands for advanced technology, I think. But as with the latest SCSI, this is a serial device. It's not using the big ribbon cables with lots of lanes. Small and fast, and only one wire of information. I'm going to talk about CAN next time. Those of you who are musicians might come across the MIDI bus. This is a similar idea, dating from the 1980s. Still in use today. You'll see ports like this on musical devices and on computer sound cards. MIDI is a true bus. You can have a bunch of devices like synthesizers and keyboards all sharing the bus, all seeing the information there. Messages, instead of being addressed to devices, they're broadcast on channels. There are 16 channels in MIDI, and devices can choose which channels they want to respond to. So you can connect your laser harp up to channel 7 and then have 3 synthesizers that are all listening to channel 7, and that will make a chorus of 3 synthesizers playing at once when you play your laser harp. MIDI is from the 8-bit age. It's all done in bytes. A message is called a MIDI byte, and they contain information like the channel, the pitch, the velocity, the duration, and then these very interesting parameters that can be used to control the actual synthesis process with your filters and your fancy synthesizer devices. Ethernet, you're probably all familiar with. In its oldest and simplest form is a true bus. Remember, a true bus has this property: every message is visible to everyone on the bus. Nowadays, Ethernet is usually used as a low level of the networking stack. When you do your networking module, you'll see TCP, IP, and everything sitting above Ethernet, which are certainly not bus architectures, but Ethernet itself is the lowest level, and it exhibits the bus properties. So raw Ethernet is much older than these higher level systems. You can use Ethernet by itself just to network a bunch of computers in the same building. At the Ethernet level, you're dealing with messages broadcast in units called frames, and they're addressed to machines on the network, which are called MAC addresses. These are different from the internet TCP IP addresses, you see. When you configure your networking card, you'll see you often have 2 addresses. You've got your internet address, and then you have this thing called the MAC address, which is the address of the underlying Ethernet hardware. So being a bus at this level, Ethernet has to take care of the usual bus problems of managing collisions, trying to negotiate people talking at the same time. It also means everyone can see everything on the bus. When I was an undergrad, the internet didn't used to be encrypted at all then, and everyone in our college was on the same Ethernet network, and it was very easy to sniff packets on the net. You could see what everyone was doing in their computers in the whole building, because it was a bus network. Nowadays we try and put encryption layers up above that. And nowadays we tend to use Ethernet as this low level, and we're going to build non-bus topologies. We're going to introduce things like switches and star topologies and higher level protocols, TCP IP, which you will study later on in your networking modules. Anyone used InfiniBand? Okay. No. So I spent some time using this. I used to work in speech recognition, running computers like this. Big grid clustered systems. InfiniBand is a bus designed to link multiple computers together very, very fast when they are physically close together. The idea of InfiniBand is you almost take the main bus out of your computer, the fastest bus you can, the Northbridge level bus, and you're going to wire that directly into the computer next to you. So instead of going through all the usual networking protocols of compiling things down and going through the bus hierarchy and putting them on a network and back up, you just connect the buses almost directly to each other. It's been described as, it's like ripping out your spinal cord and plugging it into your friend's spinal cord for direct communication between them. So you take this out of the Northbridge level. Because you're using that highly parallel bus that's really designed to go inside computers only, you're physically limited to about 70 meters of range before interference effects and everything start to creep in. So it's designed for very fast networking in supercomputer systems like this. And it's really blurring the line between a bus and a network, and it's blurring the line between what is a computer and a cluster of computers. If you really connect things at this level, is this whole room one computer sharing a single bus with lots of co-processors, or is it lots of computers wired together? Or maybe there isn't really a difference anymore between one computer and a bunch of computers. It horribly violates networking theory. When you do your networking module, they'll teach you this lovely model with 5 layers that are all supposed to be independent, and InfiniBand just rips all that stuff up to give you speed and performance in an architecturally horrible way. And as with a lot of these things, it's not really a bus, it's actually another mesh network. There is logic in there now for seeing where messages are going and forwarding them only on certain bits of wire to free up the rest of the wire for everyone else to use. So for a while it looked like InfiniBand was going to be the standard for these supercompute centers competing with Ethernet. Ethernet's actually come back now. We now have gigabit Ethernet, which is getting Ethernet up to speeds more traditionally associated with InfiniBand. And it's running in an InfiniBand-like way. So Ethernet used to come off the South Bridge. It used to sit on an Ethernet card on a PCI bus down here. InfiniBand started running here, along with your RAM and your graphics card. But now, high-speed gigabit Ethernet is also sitting here. It's copying the InfiniBand trick, and is maybe going to displace InfiniBand again. These things are always racing. There's a trend in bus design for everything to try and move up the hierarchy. You know, someone invents a new level of stuff, and we put all the old slow things down here on Southbridge, and then the designers of those things make them faster, and then they want to come up here to Northbridge. Some of the stuff off the Northbridge then migrates onto the CPU, or at least onto system on a chip silicon up there. And we're currently researching 10 gigabits per second Ethernet, so it's in interesting times in the world of bus design. Some of the general trends we see from this then, there's this replacement of parallel buses that used to look like that when I was a kid with serial buses that look like that. These have fewer wires. There's really only one wire's worth of communication going down a serial bus. There might be other wires for power supply and for differential signaling. This seems quite counterintuitive. You'd think that a bus like this is always going to contain more information than a bus like this. The reason for it is these small differences in delays. When you take a bus, especially when you take it out of a physical desktop box, the physics of each wire is going to be slightly different. They can introduce very small propagation delay differences. So the signal you send on this lane may get there a little later than the signal you sent on this lane. In the 8-bit era, when we used to use these things, that level of time delay didn't really matter. You're dealing with tiny chunks of time to do with the physics of electrons flowing down wires. But buses have been getting faster and faster and faster. When you get to around a gigabit per second, these effects tend to kick in. And you then spend more time worrying about synchronizing and compensating for these delays than the speed gains you get. Typically, you're going to get a factor of 10 or so from going parallel. And those speed gains get overwritten by all the work you have to do to resynchronize for these small delays. So what we've seen then is everyone is going back to these serial buses, but making them go very, very fast. You can take this and you can run it 10 times faster than that because it doesn't have these delay compensations, and that compensates for the loss of the multiple lanes there. It's a little bit like the CISC versus RISC debate. This is a kind of CISC-y approach, and this is a risky approach. It's a lean and mean and very fast architecture. This move from parallel to serial buses has been described as the event of a lifetime for bus engineers at Xilinx. Bus engineers aren't as glamorous as CPU engineers. You know, CPU engineers have a lot of events of a lifetime, but if you're a bus designer, you know, maybe you didn't quite make it into CPU design. You became a bus designer instead, and this is the greatest thing of your lifetime, that parallel buses have been replaced by serial buses. Another trend then is this replacement of buses with mesh networks. They reach a certain point, you put a lot of devices there, and then this mesh idea starts to creep in, that you should put in a bit of logic that each device should listen for messages for its friends and pass them on there, again, to reduce the congestion bottleneck. A bus is always potentially a bottleneck as you add more devices to it. And there's this trend of everything racing to move up the hierarchy. We keep trying to add more layers to the hierarchy to push slow devices down, and then the people making those slow devices don't want to be at the bottom, so they make them faster, and they try and jump their devices up there. And eventually things migrating onto a system on chip silicon. Everything's going to end up on one chip at the top of that hierarchy. So just for fun, let's look at some devices. Arguably, this is not so much part of computer architecture. This is the very outside, but it's good for professional computer scientists to have some understanding of what happens at the device level. Let's begin by looking at simple graphics systems. I'm going to talk about modern graphics cards later in the module. Let's look at how it used to be done as a simpler version of that. These are the graphics chips from a BBC Micro. There are 3 chips involved in this process. The BBC Micro used a memory mapping system for RAM. This is the map of the BBC Micro's address space I mentioned before, starting at 0, going up to FF. You can see there's ROMs are plugged in up there. This is the I/O section. This page was called Sheila for some reason. There's some more ROMs. Here's your RAM. Your RAM's got a stack and a heap. You'll study in programming language theory. There's some special stuff reserved for the use by the operating system down here. So to light up a pixel on a BBC Micro, you just have to store a number at one of these locations. This appears as regular RAM. The hardware is a little different because when you've written that thing to RAM, there's wires coming out of the back end of that RAM and taking it into what is called a VDU chip. It's this visual display unit, kind of the old name for a small graphics card. So this thing would read the video RAM, translate it into RGB, red, green, and blue channels, and then write stuff out to a ring buffer. At this time, the monitors were scanning cathode ray tubes, so like a sound card, you'd fill that buffer with what you wanted the ray scanner to be doing in its next scan. And then you'd have another chip. This is the actual device. This is picking up the values of that ring buffer and turning them into actual voltages to send stuff out to control the CRT out there. One of the greatest hacks of all time was the video game Elite, where they figured out that the BBC Micro had different screen modes which controlled the rate that the CRT was moving and the rate of these scans. And it was always assumed you either had to be in a high resolution mode with a small number of colors or a low resolution mode with a lot of colors. And the programmers of Elite figured out you could hot rod this to split the screen into 2 areas running in 2 modes at the same time by flipping the mode of this controller between those display types during a single scan of the CRT. This was not anticipated by the designers of the computers. It was a great example of game programmers really pushing the limits of what was possible with the hardware in that time. So nowadays, your screen probably looks like this. This is a close-up of your mobile phone. This is an LED screen. LED stands for light-emitting diodes. Remember, the diode is the half a transistor. It's a semiconductor that only allows electricity to flow through one way. And we talked about energy usage in semiconductors. When you have this one-way flow, you also have this property of giving off energy as heat or light. And in the case of an LED, this is a light-emitting diode, so the energy is given off as visible light. And you can produce these things to light up in the 3 different colors, red, green, and blue, which correspond to the 3 channels that your eye is recognizing. There's been a lot of activity in this area recently. If you look at things like organic LED and active organic LED, the phone manufacturers are really pushing different technologies. They're trying to make these as bright as possible, to use as little power as possible. There's been a lot of use of rare earth metals, so we have to go to China and mine specific bits from weird parts of the periodic table to make a lot of these devices. There are some worries about us running out of some of those rare elements. Your phone probably has 2 layers then. It probably has the LED display, and then sitting on top of that as a physically separate layer is the touchscreen layer. So your touchscreen is a transparent layer. It's separate from the LED display, and it's made out of a circuit like this containing lots of small half capacitors. Remember, a capacitor is 2 metal plates with a gap between them in an electric circuit. If you make half a capacitor, then you can sit there and wait for someone to put their finger on the top, and the skin of your finger forms the other plate of the capacitor. That makes the thing into a functioning capacitor. So you have these half capacitors sitting in a grid, and then you put in some analog circuitry and some digital logic to measure the capacitance, and that's going to tell you which of the capacitors are close to fingers. So you don't actually have to touch a touchscreen. You can be a tiny little distance away, and you'll still see the capacitive effect. All this stuff, the LED screen and the touch screen, is manufactured in a similar process to chip manufacturing. We saw this process of making masks and then chucking stuff on the masks. So there's a lot of activity in chemical engineering here, but the basic idea is you're going to design these circuits, you're going to make the masks, and you're going to chuck different elements on different layers to build up these circuits. The innovation that enabled the touch screen was the discovery of transparent metal. Usually a basic property of metal is that it reflects like a mirror. The reason it reflects like a mirror is because all the electrons in a metal are free to wander around. It makes one big metal molecule with shared electron. And a side effect of that is if you throw light at it, it has a near infinite set of frequency bands that can be absorbed and re-emitted, which means that anything conducting is also going to bounce light off like a mirror. But somehow they figured out if you, again, find this unusual metal, indium, and make it into indium tin oxide, you can create a transparent metal which allows you to do all this masking stuff on something that is see-through. And that enables you to put your touchscreen layer on top of your LED display layer to build up the touchscreen. So similar technology, again, is used in manufacturing camera sensors. We use the same sensors now both for static images and for video cameras. Any kind of digital camera is going to have a sensor that looks like this. If we zoom in on that, we see a similar structure to an LED screen. Again, this has been made through that masking process, depositing layers of different metals to make the circuits that we want. It's just the opposite of an LED screen. Now we're going to make RGB sensitive pixels. They're going to absorb these different frequencies of light and send out a digital signal, allowing us to digitize the images that we're seeing. So then we come to sound cards. Again, I'm going to show you an 8-bit approach to sound cards. We might talk later on about modern sound architectures. It's easier to understand in the 8-bit system. This is a nice example of the I/O module theory that we've talked about. You'll see in the BBC Micro there's these 2 layers of chips. This is the I/O module. So this thing's sitting on the bus. You can see this has got a lot of pins. There's a lot of address pins because it's sitting on that 16-bit bus with 8 bits of data. So this thing's going to sit there on the bus near the CPU. It's going to look for these CPU store commands, typically, that are giving sound commands. And it's going to translate those into digital voltages to control this thing. This is the Texas Instruments SN76489. This is the definitive sound of the 8-bit bleeping era. Appears in a lot of other 8-bit machines, like the Sega Master System, I think, had one of these. So this chip doesn't know anything about the BBC Micro or the Sega Master System. This chip has its own interface. You can download a data sheet telling you what voltages you have to put on these different wires to make different kinds of sounds. And it's the I/O module that forms the link to the particular computer. It's taking the addresses assigned by the BBC Micro's specific design and mapping those into voltages to give to the tone generator. This chip was pretty simple. It only enabled you to output square waves like this. This is the kind of music you would make if you were an engineer rather than a musician, because it's the easiest kind of musical signal to generate. You spend half your time outputting a 1 and half your time outputting a 0. And these are nice because you can use digital logic to output 1s and 0s. You can use all the same digital logic we've seen so far. To output anything else, like sine waves and triangular waves and saw waves, you need non-binary values. They sit outside the world of digital logic. So if you're a digital logic person, this is obviously how you would build a musical chip. The square wave has a distinctive computery sound. If you've ever played 8-bit video games, especially the older 8-bit systems that only had the square waves, this is where that sound comes from. This is why computers sound computery. They have certain properties. They have an infinite number of harmonics. They have a kind of glassy, crystally, very distinctive, but somewhat limited sound because it could only make waves that look like that. BBC Micro is a classic bit of British engineering in that it was brilliant, but it was completely mistimed from a marketing perspective. So the year after the BBC Micro, the Commodore 64 came out. Commodore had just bought MOS, who were making all these chips. They were making the 6502, the thing in the BBC Micro. So there's quite a connection between the BBC Micro and the Commodore 64. But By this time, they'd got the new chip called the SID, which was a much more advanced version of this, made by MOS themselves. And the SID chip was a proper musical, almost an analog synthesizer. It was designed by real musicians rather than by digital logic engineers. So the SID chip would let you generate other waveforms like saws and triangles, and importantly, it also let you add filters. And a filter is something that tweaks particular frequencies. If you've ever experienced the dance music effect where the frequency rises and rises and people put their hands in the air before a drop, this is done by making a filter sweep over the signal. Yeah? Emphasizing different harmonics in the series. So there's a big difference in the computer music you hear from BBC Micros and Segas and from the Commodore 64. A lot of the classic 8-bit music, I think there's a new thing now of digging out 8-bit composers and re-evaluating their work as serious art and so on. A lot of that is coming from the C64 era rather than the previous BBC Micro era, because you have that extra level of musicality. When you got to things like the Nintendo NES, they got even fancier, and you could define your own waveforms. You could go in and choose exactly the pattern you want and the kinds of harmonics there. So again, you got another wave of composers coming from there. All of this is no fun on a modern sound card because they just give you a big ring buffer and you can write whatever waveform you want. So you could produce square waves and saw waves, but there'd be no particular reason to. You can just create regular real-world audio. So the distinctive sound of computer music has somewhat disappeared unless you're doing it deliberately to be retro, just to sound like the older hardware that really had to sound like that. Let's have a quick look inside your keyboard and your mouse. This is a keyboard teardown. In the old days, this was simple. Every key would be memory mapped, so there'd be a particular location that appeared as a bit of RAM, and if a key was down, that location would have a 1 in it, and if the key was up, it would have a 0 in it. So to read your keyboard, you could just do a load from that part of RAM, effectively, and see whether the key was up or down. Nowadays, things are much more complicated. You can see there's a whole chip inside your keyboard. So there's a small embedded computer in your keyboard. Yeah. This is looking for those presses coming in. It's going to translate them into an ASCII-like serial encoding, and it's going to convert them to USB messages. There's a whole load of work you do to read and write the USB protocol, and it's going to stream those out over USB. The advantages of that is you get this standardized I/O. You don't need a special I/O module for your keyboard anymore because it runs over the regular USB system. So there's a little computer inside your keyboard. Now, again, is this a computer? Is it a device of your regular computer? What's the difference between one big computer and two small computers? The same things happened in your mouse. So mice used to be quite simple. You had a rolling ball. You had some usually optical odometers. You remember the odometry from the Roman travel cart, dropping the rocks to measure distance? Exactly the same principle, measuring how many rotations. So look, here's the ball goes around, it makes this thing rotate. That is an optical device with some black and white bits, and you count how many times that goes around. Again, there's a chip that is counting those and turning them into speeds, and it's going to chuck that. Nowadays, it's going to convert it to USB protocol and send it down the wire. When you get to optical mice, these are really, really fancy. If you think about what an optical mouse is actually doing and try and do this in software, you will have a very difficult time. It's based on a machine vision principle called optic flow. You're trying to see how the image underneath it is moving around. So imagine taking a webcam and moving it over a desk and then trying to line up those images and looking at how they're moving over time. Doing that in software is very, very hard. There are machine vision tools like OpenCV library that try to do this in software. It's still a very intensive process. It's still a research process. And what you find in your $5 mouse is a dedicated digital logic circuit. This is something you could build in Logic Sim again. This is a dedicated circuit dedicated to doing that optic flow algorithm very, very fast and doing it in parallel. This is a parallel computer sitting inside your mouse, okay? Capable of doing things that are very hard to do with state-of-the-art machine vision libraries in software. So current trends across I/O then. Buses and I/O are important. They've become a lot more important in recent years because they're bottlenecks. You can hot rod your CPU as much as you like. If this stuff is slowing you down, that becomes the limit. So there's been a lot going on over the last year. Everything is racing up this bus hierarchy. Everyone's trying to get up there, and then they put another layer in the hierarchy, and then everyone races up there again. There's this consolidation to a few standard protocols. We don't want every device to have its own IRQs on its own module anymore. We want to use things like PCIe and USB to standardize that stuff. But the downside of that is this conservative effect. It's difficult to innovate if everyone's using the same standard bus. We're seeing a lot of buses replaced with mesh networking. Parallel buses are turning into these faster, lean and mean serial buses. And a lot of logic is getting pushed down from the CPU into the devices. They started putting things in I/O modules, but now we're seeing little embedded and parallel computers inside your keyboard and inside your mouse. Those two trends are predictive of the next decade of computing. Everything's going to be either embedded or parallel or both, and those will be the topics of the next 2 lectures. I'll see you then. Thank you.